All right, today we're going to focus on organic reactions. We're going to be kind of combining what we did in the last 2 days with identifying different types of compounds, but now actually putting it and applying it. All right, the first type of reaction we're going to talk about is combustion. We've actually talked about this earlier in the year, but now that we know a little bit more about hydrocarbons, it makes a little bit more sense to bring it back up here as well. So we react hydrocarbons with oxygen gas to produce carbon dioxide in water. Now this reaction has to happen at high temperatures in order to form carbon dioxide in water. This is a common reason due to combustion why alkanes are also used for fuels. If oxygen is limited, we'll only be able to produce carbon monoxide or soot, which is pure carbon, that can get formed. So here is just, again, a little bit of more of a graphic representation of combustion. Here we have methane reacting with oxygen to produce carbon dioxide and water. And then, again, here below, you would need to be able to recognize that you have a hydrocarbon and oxygen and be able to come up with the products of carbon dioxide and water. All right, our next type is substitution. This is going to look very similar to the next reaction we're going to do called addition. So it's important to know a couple of different things that are specific to substitution. First off, this is a reaction that only occurs with alkanes and saturated hydrocarbons when an atom or group is replaced by another. That's where that substitution part comes in. So here we're looking for an alkane reacting with a diatomic element. Again, we're going to be doing addition next, which is going to be with alkenes and alkynes. So the big thing to look for with substitution is that one of our reactions is an alkane. And then it's going to produce a compound in which the diatomic element has been substituted at the end of the alkane, which is important. We're only going to be able to replace one hydrogen at a time. So for this, we can see that fluorine is reacting with ethane. You can see that we have replaced a hydrogen here with fluorine, and then the remaining fluorine has bonded with that hydrogen. Again, here we have methane reacting with chlorine. We're going to replace one hydrogen with the chlorine, and then with our leftover HCl, in which the hydrogen that was substituted out is now reacting with that leftover chlorine. So the big thing is that hydrogens get replaced one at a time. So we're only going to see one diatomic element or an atom from it attached to the molecule. And the diatomic elements will usually be added to the ends of the molecule. So we're usually looking for it at the first or the last carbon in a chain. All right, so addition, this is going to look very similar to substitution, but a couple of key characteristics. This is only going to occur with unsaturated hydrocarbons where we have that double or triple bond. The atoms are added across that double or triple bond, so they're added next to each other. So here we're going to have an alkene or an alkyne reacting with that diatomic element, and again, this alkene and alkyne is what makes addition reaction different than substitution in terms of how we look at it. There's a lot of fundamentals that are different as well. Now the products are going to be an alkane because we've now, if for an alkene breaking its double bond to bond with a diatomic element, we're going to end up with an alkene with a diatomic element added next to each other. And let me show you what that looks like. Here we have our double bond. The fluorine is going to add across the double bond, breaking the double bond, and then each fluorine bonding with the carbon. So here again, we're adding across the double bond, breaking it, and then the two fluorines are added next to each other. Same thing with this example with ethene and chlorine. The chlorine gets added across the double bond, breaking the double bond, and then each bonding with the neighboring carbons. So the multiple bond is broken, the halogen adds on the site of the newly available bonds, and the fluorines in this top case get added next to each other. So substitution was added one at a time. Here we're adding them both at the same time across a double or a triple bond, and then they're on neighboring carbons. All right, we're going to move on to esterification. This is going to involve an alcohol and an acid. So you have to be able to use table R to identify your alcohol, and then we also will have an acid there. And then our products are going to be an ester, which is easy to remember with the name of the reaction, and water. This is a very slow process that requires an acid or base catalyst. So this is sometimes considered a type of dehydration or condensation when we have to use an addition to this catalyst. So here we have the reaction. We have our ethanoic acid, that's our acid, and then we have our alcohol, in this case 1-butanol. This H2SO4, our sulfuric acid, is our catalyst, and then we can see that we have produced our ester, so butyl ethanoate plus water. Now, what I want you to notice here is how these have combined. We're going to if I look at this top example, combined the OH from the alcohol and the hydrogen from the acid, that produces the water, and then this remaining oxygen from the acid has combined with the carbon chain of the alcohol. Same thing down here, I have propanoic acid and methanol producing my ester, which is methylpropanoate. The hydrogen from the acid and the OH from the alcohol are going to react to form water. The oxygen from the acid is then going to combine with the carbon chain in order to produce our ester. So you need to be able to work backwards in terms of, if I give you the ester, coming up with the original acid and alcohol, so knowing where the breaks in the compound. So in this case would be between our CH3 and the oxygen here. And then also, if I give you the acid and alcohol, getting that product of our ester, knowing what to basically take off for water and then how to combine those two molecules. So we'll spend a lot of time in class going over this, but make sure you've circled these parts or highlighted where the water is forming from and so on, so that you can start to see kind of where the breaks are. So like here, if I look at the butyl ethanoate, it would break between this oxygen and carbon to make my original acid and alcohol, and then here again would be between that CH3 and the oxygen. So just some things to note into your note packet. If long chains acids, which are known as fatty acids, react with glycerol, esters known as lipids are formed. Fatty acids with many double bonds make unsaturated fats, usually lipids. Animal fats are usually solid and saturated with few double bonds. So a lot of the kind of chemistry behind a lot of these common terms that you've heard of, such as fatty acids, unsaturated fats, lipids, animal fats, have to do with the types of bonds that are within them and how they'll react. All right, we're going to move on to saponification. This involves a reaction between a base and a fat, making glycerol and soap. So this is the production of soap. Saponification is the hydrolysis of a fat, which is an ester, with a base. Soap is the salt of a fatty, aka long chain acid. All right, so here we have our base that's going to react and make glycerol, and then this is the formula, for example, for soap, sodium stearate. So here we have, which you can see with this expanded structural formula, the formula for soap, which is a very long molecule that is nonpolar at one end and polar at the other. The nonpolar end attracts nonpolar substances such as dirt and oils. The polar and ionic end, so here we have the ionic part of the molecule, attracts the polar solvents such as water. So that's why we're able to use soap to help wash dishes, break different particles apart, instead of just using water by itself, since we know that only likes dissolve like. All right, we now have fermentation. This is going to be oxidation that occurs without oxygen. It requires enzymes made by living organisms to act as our catalyst. So this is another reaction that involves a catalyst. So we have sugar reacting with a catalyst, which is usually a yeast enzyme, to produce an alcohol. So here we have sugar. The yeast enzyme is our catalyst, which is written over the arrow because it's not going to directly make or participate in the formulas of the products. It's just going to speed up the reaction, producing our alcohol, and then usually we do have carbon dioxide gas left over. Again, here we've produced the alcohol through fermentation using a yeast enzyme. And then finally we have polymerization. This is when small molecular units are going to produce a long chain of repeating units. A polymer is a long molecule of many repeating units, which we call monomers. So monomers are like these very small units that then connect into a very long chain. Polymerization is the process of putting them together. So here we have 18 individual units. A is just representing a monomer that through polymerization is going to make a very long chain of these single units. It's often seen as this formula at the bottom. I have a certain number of these smaller units, and then those through polymerization make a repeating long chain. So the number of units then get all connected, which is why we see it down in the right hand corner. Instead of writing all of them out, this is just a common way that we show this repeating unit and how they're all connected together. And then just a couple little facts to note. We have various natural polymers and synthetic polymers that are used in everyday life. We have natural polymers such as proteins, starches, and cellulose. And we also have synthetic polymers that include polyesters, nylon, polystyrene, and polyethylene, which is made of ethane. All right, so that was a bunch of different reactions. I would highly suggest looking back over each of them, looking at each of the reactions, starting to pick up on some, common things that occur with each reaction. And then tomorrow in class, we're going to be applying this to examples, writing reactants, writing the products. So it's definitely a little bit of work, but especially if you've been keeping up with all the different types of compounds the last few days, you'll be all set.